2.4, heap properties. Now we need to study in order to make the heap data structure to help us do some, special data organization, we need to provide it. We need to assign some special property to the heap. So let's look at that part. Relationship among heap nodes. We know from a binary tree, parent-child relationship should be specified in some way, right? But in an array, how can we specify parent-child relationship? So that is the key. So let us do that part first. A binary tree is stored in an array by imagination. So at this point, we cannot have a specific binary tree, graphically displayed there. Here we can only imagine the data stored in an array has certain binary tree structure. But that binary tree structure, we need to make that part. So right now we do not have that part, but we will add that structure to the array. All right, so let's look how to do it. First, let's look at each node. Each node has its own index corresponding to the location in the array. All right, now how do we describe relationship between two nodes? Parent-child. So it's, the most important relationship we want to describe. Parent-child relationship. We want to use some simple way to do it. Parent-child relationship. Here, so there is a simple way. Parent-child relationship. All right. Here, let's consider a typical situation. Parent node P with index I, then left child, we use L, but we make it index 2i. Index 2i. Right child, we make it index 2i plus 1. All right, so we pick these three nodes if their indexes, P, L, right, their indexes satisfy that pattern, I, 2i plus 1, then we can treat these three nodes as parent, left child, right child, that relationship. That kind of description, pretty natural, right? Okay. But for this kind of assumption, arrangement, there is one little thing we need to consider. That is, the I cannot be 0. The I cannot be 0. Okay, You can think about why I cannot be 0. Okay, why I cannot be 0. If I equal to 0, I and 2i are the same, right? I equals 2i. Parent, left child, the same node. We do not allow that happen. We do not allow that. Okay? So for that reason, we need this condition. That means the first element in the array, first element, 0 location, cannot be used in this heap. Yeah. The first element in the array cannot be used, in the heap. Yeah. Although you can use it to store some other information, but do not make it any node in the heap. Okay? Yeah. You can use for other information if you have something to store there. Yeah. But do not use it as your heap node. Yeah. All right. So with that kind of thing, now, next, because we need to make this data structure to support sorting. So we need to provide it some order-related property. Yeah. Here, this kind of parent-child relationship, not order-related, right? Not order-related. We define parent-child relationship. But for the values stored in these nodes, we do not say anything. We do not say anything on the values stored in those nodes. But next, we need to look at the value part to do the ordering. Order the values in the array. Yeah. All right, so let's look at that. Two types of heaps. Okay. Max heaps and min heaps. Maximum, minimum heaps. Two different types. Okay. Yeah, but similar, quite similar. Yeah. Just orientation, direction different. Yeah. All right. Max heap property. Yeah. The value in the parent node a of I should be greater or equal to a of 2i, left child. The value stored in the left child. Also, the value in the parent should be greater or equal to the value in its right child. If this property is true everywhere in the heap, then we call it max heap. So this heap has the max heap property. So we can call it max heap. Now, similarly for the min heap, yeah. So you can see we just changed the direction of the inequality. Yeah. Value of the parent should be less than or equal to value of the left child, also value of the right child, the main heap. Yeah. But for this class, we only look at the max heaps. Now, that's enough. Now, for the main heaps, we just change the direction of the inequality. Yeah. We can easily get that. Yeah. So we do not need to repeat it. Yeah. All right, next. In order to visualize heap structure, I like to show you a simple example. Yeah. Here, so let me show you this simple example. Yeah. Look at the array of numbers, and we arrange in this way. Yeah. So we are given an array with 10 elements. Here, 10 elements. Yeah. 10 elements. Okay? Yeah. 0 location we do not use. So the largest number is stored in the index 1. Yeah. Then 2, 3, then in this way. Yeah. So you can, if we use the max heap property, you can check it satisfies max heap everywhere in the heap. For example, these 3 nodes, 16 greater than 14, also greater than 10. Okay, yeah, the first check. Second, 14 greater than 8, also greater than 7. Okay, yeah. Third, 10 greater than 9, also greater than 3. All right. Next, 8 greater than 2, and also greater than 4. The last one, this one, there is no right child 7 greater than 1. Yeah, that's all we need. So we can say this is a max heap. All right. But how do we store? So this heap structure, when we visualize it, it's a binary tree structure, but we store it in an array. So we want to look at in the array, the state in the array. Yeah. All right, so here, this is the array. 0 index location, leave out. Yeah, nothing there. Then we need 10 positions with index from 1 through 10. Now we do the arrangement. Yeah. Node with value 16, first one. Then 2 child nodes at location 2 and 3, 14 and 10. Then for node 14 at location 2, 2 child nodes at location 4 and 5 with value 8 and 7, and so on. Okay? So we can do this kind of, arrangement, yeah, like this. So you will see, finally, we will arrange all 10 elements in the array, pretty nice. Yeah. No gap, no, complicated things we need to do. Yeah. So very natural. Yeah. All right. So next, let's look at maintaining the heap property. So while we talk about that, remember we have that dynamic data manipulation task. We need to do that part. Yeah. When you do that part, then you need to consider how do you maintain the heap property after you get a new dynamic data. Yeah. Yeah. So let's look at this. Yeah. When there is new item added into the heap, then the max heap property could be violated, could be very likely get violated. Okay? Yeah. Due to some operation like insertion, deletion, that kind of things. Yeah. After that, after the violation, we need to fix it. We need to do some manipulation, arrangement, recover that heap to the max heap. All right, so how to do that? Yeah. Here, let me use a general portion of the heap to show the idea. Yeah. Here, we have 3 nodes, P, L, R, typical location. We need to consider violation. Yeah. All right. Suppose there is a violation, occur in this part, right? So then we need to fix it. Okay? So we need to do the fix. Yeah. All right. So when we do the fix, first we need to do the local fix, right? So we need to make sure between these 3 nodes, P, L, R, they satisfy the max heap property. If not, we need to swap. Now, we need to swap. No, we need to do some appropriate swap operation to recover the heap recover the max heap property in this big red circle. After that, then we need to consider each subtree left subtree and the right subtree, because after we make the swap operation, we may have violation either in left subtree or in right subtree. For example, if our swap get a left node, child node involved, then we may need to fix the left subtree. If our swap get right child involved, then we may need to continue to fix the right subtree, and so on. Okay? Yeah. All right. So local fixing operations, swap. Yeah. We will see the detail next slide. Yeah. After that, check for violation globally. Yeah. So that means the part that we touch, if we touch it, yeah, if we, change the value of the node, yeah, here, these two places, then we need to keep checking the whole subtree, or, the same way, parent, left child, right child relationship. Yeah. Keep going until we reach the bottom. Then we can stop the checking. Yeah. All right. Later, in my next video, I will use a concrete example to show you the fix. Okay? All right. Now, local Heapify operation. How to do the swap operation? We call it local Heapify operation. Yeah, pretty simple. Yeah, so you can see pretty simple. Yeah. All right. Recursion approach. Here, we do recursion. Yeah. All right. In the current iteration, PLR, yeah, we check the max heap property. Okay. We do the appropriate swap, then after that recursion. Okay. All right. So let's start now. Comparison. If A of I less than A of 2I. Okay. Yeah. A of I. We know there is a violation, right? A of I, the value of the parent node is less than the value of the left child node. Okay. When we detect that violation, how do we do it? We store 2I index temporarily in largest. Temporary variable, largest. Okay. So we want to use this variable to store the largest value of the 3 nodes. Okay. Yeah. Then else, now, if A of I greater or equal to 2I, so else case, then we store I value, parent, I index in the largest temporary variable. Okay? That's the first part. We only check parent left child relationship. Yeah. Then we have second half. The second half, this time we compare the value of A of largest and A of 2I plus 1 right child value. If less than, then we update largest variable by 2I plus 1. We know right child has the largest value. Okay. Else, yeah, okay, yeah. That's done. Yeah. Because after that, our largest variable stores the index of the largest value of the 3 nodes. Okay, 3 nodes. But that largest variable could store I index, right? If it's I index, do nothing. Yeah. It's no violation. No violation. But if not, then if largest not equal to I, then we do swap operation. Swap A of largest and A of I. See? Pretty simple, right? One swap. You only need to do one swap. And you only touch one of the child nodes. You do not touch, what I mean, you only change the value of one of the two child nodes. Although when you do comparisons, you need to compare both. Yeah, you have to compare. But when you do comparison, you do not change the value, right? Yeah. But this only the swap operation, you change the value. Okay? You change the value. Value of the child node. Although we also change the value of the parent node, but because here we want to look at the child node, because this will tell us tell us the next step, right? Next step. Next step, which subtree to fix, right? Yeah. Next step for the subtree to fix, right? Because only when we change the value of the child node, then we may cause new violation in that subtree. So that's why, yeah. So this swap operation tells us which subtree to continue the checking. We need to do the, max heap property checking on that subtree. The root value of that subtree is changed. Okay, yeah. So that's the meaning. So now after that, if we do this all the way down to the bottom level, you need to reach the leaf level to finish your checking. Finish your checking. Okay, all right. Yeah. So that's the heap property, local Heapify operation. With this operation, we can recover the max heap structure with, the important thing is, with how much cost do we pay? Big theta of log n. This, the height of the binary tree, log of n. So you can see this is the fixing cost we are willing to pay. We are willing to pay, not big theta of n. We are not willing to pay big theta of n. So we are willing to pay this fixing cost. Okay, it's acceptable. Yeah. Other than this, it's not acceptable. Okay, all right. So let me complete this video B.4.